Hi and welcome to lesson 12.2, which is all about experimental probability of simple events. And our central question is, how do you find the probability of a simple event? Seems pretty obvious there. Well, on our explore activity, we're going to be finding experimental probability. You can toss a paper cup to demonstrate experimental probability. Consider tossing a paper cup. Fill in the outcome of the table with the three different ways a cup could land. Okay, I got a cup right here. Look at that. Ooh, cool. Hey, that's coffee, probably, hopefully. Anyway, now the outcome could be open end up. It could be open end down, or it could land on its side, like this. And I tossed the paper cup 20 times, and I recorded my observations. So open end up didn't happen at all. Open end down happened twice, and on its side it happened 18 times. Do the outcomes appear to be equally likely? Certainly not. It's skewed here. Describe the three outcomes using the words likely and unlikely. On its side is most likely, right there. Open end down was somewhat likely, probably unlikely, but anyway. Open end up definitely was unlikely. That hadn't happened at all. Use the number of times each event occurred to approximate the probability of each event. So we have the outcome. It's 0 out of 20, open end down, 2 out of 20, and on its side, 18 out of 20. Let's make a prediction. What do you think would happen if you performed more trials? I think the probability of the cup landing outside would increase, even more so probably. And the sum of the probability, what is the sum of the probabilities in 3? Well, the sum is going to be 1. So because the probability of from here of all the events, because if you have 0 plus 2 plus 18, that's 20. That's 20 out of 20, which is equal to 1. Okay, next, we're calculating the experimental probability. You can use the experimental probability to approximate the probability of an event. An experimental probability of an event is found by comparing the number of times the event occurs to the total number of trials. When there is only one outcome for an event, it's called a simple event. And that is what was happening earlier. For our simple event, we're just looking for our one item. What was the result? So for our experimental probability, the number of times an event occurs divided by the number of trials is how you calculate the experimental probability. And each item in here is a simple event where we're looking for an outcome for an event. One outcome for the event. I know that in here, in this one, there were 3 outcomes, but in each case, we're looking for a particular outcome. Did it end up? Okay, what was that probability? Did it end up down, and was it on its side? Next, Martin has a bag of marbles. He removed one marble at random, recorded the color, and then placed it back in the bag. He repeated this process several times and recorded his results in the table. Okay, here's the results. The frequency means how many times each marble was picked. Find the experimental probability of drawing each color. Identify the number of trials. So how many times did he do it? Well, 12 plus 10 plus 15 plus 13 is 50. So he did 50 trials. And complete the table of experimental probability. Write each answer as a fraction simplest form. So red happened 12 out of 50. So there's the 12 out of 50. Blue happened 10 out of 50. There we go, simplified to 1/5. Green was 15 out of 50, simplified to 3/10. There's a 15 out of 50. And 13 for yellow out of 50. That's already simplified. And they say also substitute the results recorded in the table. You can also write each probability as a decimal or a percent. That is, for instance, I know, I'd multiply that by 4. So this is equal to 24%. This is equal to, that's out of 100 for percent. So that's 20%. and this is 30%, and this is double that, so that's 26%. Remember, percent means out of 100, so I just had double that to get the percentage. Let's communicate math ideas. What are two different ways you can find the experimental probability of an event that Martin does not draw a red marble? One way, you can add the frequencies for blue, green, and yellow, and then find the ratio of the sum to the total number of trials. So you can add blue, green, and yellow, and rise a ratio of the total number of trials. So you can have what? That's 25 plus 13 is 38. So that could be what? 38 out of 50 if you did that. The other way is you can use the complement by subtracting the probability of red from 1. So we could take that right there, and 1, it would be 50 out of 50 minus 12 out of 50, and there you would get brought back to 38 out of 50. So there's two different ways of doing that. Okay. Next, we have a your turn question. You should try this on your own before I go through all the details. You hit pause. A spinner has 3 unequal sections, red, yellow, and blue. So they're not the same size. Think of a spinner, and maybe it's like this. I don't know, something like that. They're different sizes anyway. The table shows the results for Nolan's spins. Find the experimental probability of landing on each color. Write your answers in simplest form. Well, first we have to add them all up. And that total is 30, because 10 plus 14 is 24, plus 6 is 30. For red, it's 10. 10 out of 30. And that simplifies to 1/3. For yellow, it's 14 out of 30. That simplifies to 7/15. And for blue, that's 6 out of 30, which simplifies to 1/5. Next, we're going to make predictions with experimental probability. A simulation is a model of an experiment that would be difficult or inconvenient to actually perform. You can use a simulation to find an experimental probability and make a prediction. In example 2, a baseball team has a batting average of 250 so far this season. What that means is it's 250 out of 1,000, because that's 250 thousandths. I can knock the zeros out. So that looks like they hit 25% of the balls. 25% of the time they get a hit when they come up to plate. This means, 25% chances at bat. Yeah, hello. Use a simulation to predict the number of hits the team's players will have in their next 34 chances at bat. So the batting average is, just like I wrote, 250 out of 1,000, which is simplifies to 1/4. And they have a standard deck of cards has 4 suits. And I've mentioned that in an earlier lesson. They have hearts, diamonds, these are the red, and spades and clubs are the black. Since 1/4 of the cards are reds, you can let hearts represent a hit. Diamonds, clubs, and spades represent no hit. Perform the simulation. Draw a card at random from a deck. And here is my deck of cards. And not a wonderful deck. I should put that like that. So if I draw this card like this, that's black. That's not a hit. If I did this, that's not a hit. That red card is, I'm sorry. It's, so a heart. Okay, so that's a heart. So that's a hit. And that is how the simulation goes. So what we have is continue until you have drawn and replaced 34 cards in all. Okay. So they did 34 cards right here. And we have H is for the heart. So all of these represent the hits. And the others, and they even tell you here, H is for heart, D is for diamonds, red, but not the heart though. C is for clubs, and S is for spades. So these are the times that it simulated a hit. make the prediction. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hearts. Since there are 11 hearts, you can predict the team will have 11 hits of the next 34 chances at bat. 11 out of 34. So, we have our your turn question. A toy machine has equal numbers of red, white, and blue foam balls from which it releases at random. Ross wonders which color ball will be released next. Describe how you would use a standard number cube to predict the answer. Remember, our number cube is one of these. So how would you use this? Well, you can let numbers 1 and 2 represent red, 3 and 4 represent white, 5 and 6 represent blue. So you've split this up into 3 equal parts for the number cube. Toss the cube 50 times to determine the experimental probability for each color and predict that the next ball will be the color with the greatest probability. Though, at this point, it looks like it's pretty even. But anyway, that's what you have to know about the experimental probability of simple events. Thanks for watching.